The final module of Chapter 20, which is Module 9, is now going to look at a variety of additional examples of Ito's lemma. We ended Module 8 with the example of the process followed by the natural log of the stock price, and saw that when S is geometric Brownian motion, log S is arithmetic Brownian motion, and we found out the origin of that mysterious reduction of minus a half sigma squared in the drift of the arithmetic Brownian motion. In this module, we'll look at some other examples. The first example we'll make of the Ito lemma is valuing a claim on a security defined as the security to some power A. So you can think of this as more of a mathematical exercise than a security that you might expect to be trading on the street. So, for example, A could be square or cube. We want to claim, value a claim which will pay the value of the cube of the price of a stock at time t. So we'll go back to the typical process of a stock with a instantaneous return of alpha. Delta is the dividend return. So this is the again the price change of a unit of stock, so that we only reflect the capital gains in the drift, and then we have our usual volatility. So we might now want to value a claim on a power of S rather than something simple like a call on S. So this is more complicated by its nature because it's a nonlinear function of S. So S squared might be an example. What would be the value of a security which at time t pays you the price of a stock squared, for instance? So here's a proposition which summarizes the result. It's a bit of a complicated result to state. The relationship between the two statements is simple. It's only one of these that we need to do some work to derive. And it says that at time 0, a claim that pays a value of a stock to some power A at time t has a prepaid forward price given by this formula or a forward price given by this formula. And again, you recall the forward price is the price we would agree to today that would change hands at time t for delivery of the st to the a power, whereas the prepaid forward price is the price that changes hands today in return for a promise of delivery of st to the a power at time t. The relationship between the prepaid and the forward price is nothing more than a discount factor to reflect the time value of money. So clearly, if we can derive either of these formulas, the other one is automatic, because the relationship between the prepaid forward and the forward typically reflects nothing more than the discount by interest. So we'll be working on the forward contract. So what we're going to do is apply Ito's lemma to we're using the notation C of st as if it's an option, but it's just a function. C of st, the function in the Ito lemma, is being defined as s to the a power. So we can calculate some derivatives of s to the a, in particular the s derivatives. It has a 0t derivative. So when we apply Ito's lemma, we get the following, namely that we get the derivative of the function ds. We get the second derivative of the function times a half with a square term, and then of course the t derivative of c is 0, so there isn't the expected value of c sub t dt, right? That's gone because it's 0. And then if we simply we can then implement you notice we have a ds here. We can calculate the sigma s squared, just multiply it out, factor it through, and we get this final expression that the process followed by s to the a has a first of all, it's a multiple of the process ds over s that includes both a dt and a dz term, and then it has an additional drift term that comes out of the second derivative. We can then simply expand the ds squared term. Go back. Sorry, it's not a ds squared. It's just a ds term. We just simply insert what ds is, multiply it all out, and we get this is the process. And what we see is that the ratio of ds to the a divided by s to the a is arithmetic Brownian motion. The ratio of the differential of s to the a to s to the a is arithmetic Brownian motion, so s to the a follows geometric Brownian motion, just like s does. So what we've now concluded is that Ito's lemma tells us that if s follows geometric Brownian motion, every power of s also follows geometric Brownian motion, and we now have here a new drift term. Remember, the drift term of geometric Brownian motion was just the alpha minus delta, and the risk term is a sigma. So the exponent of s manifests itself as a multiplier in the risk term, and it manifests itself in a somewhat more complicated way as a multiplier of the original drift term plus an additional drift term.